As we begin our study of rotational dynamics, the study of why things rotate the way they do, I thought it would be good to start with a different kind of introduction. Rotational motion is full of many counterintuitive, amazing, and sometimes difficult to explain things. So I thought it would be nice to begin with a selection of videos that show you some of these things. Some of them we'll talk about in this course. Some of them you'll talk about in later courses once you've gone through some more math. Let's start with the curious case of things standing up on their ends when they're spinning. Here we have it first for eggs, shown to us by the physics girl, and stand-up maths.
But watch what happens when you spin it lying down. It stands up. That is, if you start it spinning along its minor axis, it'll rise up and spin along its major axis.
Behold what happens when you spin an Easter egg. Look at that! It flips up and it spins on one end.
These spinning eggs are related to the Tippy top, which is an always fun toy that starts out spinning one way and then flips over to continue spinning on its stem. Check this one out.
There she blows, upside down.
And here's one from the physics girl.
Still, you ain't seen nothing. This is the famous tippy top. Not only does the center of mass rise up, but the whole thing flips over. If your mind is blown, you're in good company. Well, me. But also, here are two Nobel Prize winners and quantum physics pioneers playing with a tippy top.
And here are a couple in slow motion. One of my favorite rotating toys is the so-called Rattleback, which spins happily one way, but if spun the other way, it begins a rocking motion and then returns to spinning in the original direction. Check it out.
So I'm going to just do it again. So let's go anti-clockwise. Happily spins until wind resistance, air resistance, friction stops it from spinning. And what I'm going to do is spin it the other direction. And as you can see, quite quickly he's unhappy with that and starts to rock. And that rocking motion is then turned, again with the curvature of the back of this pebble-shaped device, into motion. So it actually rocks itself to spin only in one direction.
Vladimir Krasnikov in the late 80s came up with a lovely version of this where, with a perfectly symmetrical hull, which this one's got, it's got off-center weighting due to these turtles. If I set them like this, it wouldn't rattle back if I put the turtles in the middle. They have to be off-center like this, and then they'll rattle back. They don't like going backwards, incidentally, so they'll turn around. And notice what's happening here, because this is a particularly good one. This actually does at least 3 or 4 motions. The first primary motion, when it stops, is to rattle back end to end. And on the second reversal, it'll rattle back from side to side to side. So let's see that again. It's end to end. Now it's rattling side to side, and it's re-reversing. And sometimes you get an extra one just going that way. It's superbly balanced, that one there.
The brilliant engineer/woodworker Matthias Wandel asks and then answers this interesting question.
If I throw this frisbee, it flies fairly level. But if I just throw a flat wooden disc like this, it just always dives to the left. Why the heck is that?
Gyroscopes are one of the most important components in most modern-day control systems. Here we have a bicycle wheel gyroscope from the folks at MIT. Veritaserum has this cool video on a consequence of the intermediate axis theorem. Now that we've seen some of that interesting stuff, let me introduce you to some of the variables and equations that we'll use as we get into rotational dynamics. We'll talk about the equations in much more detail as we come to them. I just want to introduce them to you here and make a few comments on them. Let's look at the variables first. Here's the table that we have been writing down so far. Instead of position r, we have theta. Instead of velocity v, we have omega, the angular velocity. And instead of acceleration a, we have alpha, the angular acceleration. And now for the new quantities that we'll encounter in rotational dynamics. The first is force, and the rotational equivalent of that is what we call torque, indicated by tau. And then there's mass, which has a rotational analog of moment of inertia, capital I. Momentum, P, has a rotational analog of angular momentum, capital L. And there's translational kinetic energy, which has an analog of rotational kinetic energy. So those are the variables that we'll come across as we go through the rest of this course. Let's write down some of the equations now. If we write down Newton's second law, the sum of the forces equals the time derivative of the momentum, or if mass is constant, it equals ma, then we might suppose from analogy using our table that if we add up all the torques acting on an object, it'll equal the time derivative of the angular momentum. And if the moment of inertia is constant, that would equal I, the moment of inertia, times alpha, the rotational analog of mass, times the angular acceleration. We can do a similar thing for the momentum p. It equals mass times velocity. So by analogy, the angular momentum L should equal the moment of inertia I times omega, the angular velocity. The translational kinetic energy is 1/2 mv squared. So again, by analogy, the rotational kinetic energy should equal 1/2 I omega squared. Now these equations are all good and useful. The point that I want to make here, though, is that none of them are actually true in general. We'll use them in this course, and they'll apply in this course, but it's important for you to know that there are conditions that have to be met before these equations are valid. It's going to be fun for you as you move on to higher level courses to look at more general equations that are always correct. Let me end this one by giving you two expressions that are always true in this course and every other course. They're definitions. I want to give you the definition for torque and the definition for angular momentum. The definition of torque is R crossed into F. Torque is what's called the moment of force. That's a definition. The definition of angular momentum, L, is R crossed into P. Angular momentum is the moment of linear momentum. That's also a definition. So both of these things, being definitions, cannot be untrue. They're always true. So we'll leave this one here. In the next talk, we'll go over some details dealing with the moment of inertia, I. So I'll see you over there in a bit.